Okay, let's continue with the calculation of terminal velocity of a raindrop. Terminal velocity, which is when the force of gravity balances the drag force. Before going to explanation, let me show you some full slide here, then go in the detail, talk about detail of this slide. You saw that when a water drop comes down from cloud to the ground, its size gets bigger and bigger, and then due to the resistance, air resistance, as Brock said, its shape morphs, and again it's divided in smaller droplets, and finally it reaches to a maximum size of possible. And also, you know that when it comes down at the beginning, the velocity is zero when it is within the cloud, but after having the shape of a drop and getting big and come down to the earth, on the earth, its velocity increases up to reaches to a terminal velocity, a maximum velocity, which is called terminal velocity. And then the journey is continued by a constant velocity of terminal velocity. So why velocity remains constant? This is due to the balance between the forces that creates this motion, which is gravity force, and the forces that resist the motion, which is air resistance. Okay. So when we have such a balance, we can use in fluid mechanics, you also saw the balance between different equations. Balance means sigma F equals to M equals to 0. Okay, and negative force equals to positive force, or pushing equals to resistance forces. Now we should know which forces acts on a raindrop when it comes to the ground. Okay. Here in the figure you see a water drop. It has a sphere shape, and in this figure you see the forces that acting on this drop. We have Fg, gravity force, comes from the weight of drop, yes? We have Fg downward. Fb is called buoyancy force, which is called, which is a force of medium. Here the medium is atmosphere, and also it is, I will talk more about buoyancy force in fluid mechanics, but this is force due to displacement of air. When drop comes 1 centimeter down, it means that air should go 1 centimeter up. Therefore, this is called buoyancy force. And let's just a small, another easy example. Have you ever feel that you are lighter in water when you see that you are lighter? When you are in atmospheric condition, you feel your exact weight, maybe 60 kilogram, but you are lighter in the water. Why? Because of buoyancy force, you think that you have less weight, lower weight. So this is called buoyancy force. And when you go to the, for example, a swimming pool, some water goes up. If it is completely full, up to the edge of the pool, the amount of the volume of water that goes up should be the same with the volume of your body. This comes from the buoyancy force. The other force is resistance. Because of this drop surface, lower surface and sides, is in contact with atmosphere, and there's a resistance which would like to stop this motion, a kind of friction, which we call drag force. Okay, drag force. So here you also see the volume of a sphere, which is PD to the power 3 over 6, and we have the area of the or cross-sectional area of a drop, which is PD square over 5. Okay, cross-section, this area, which is perpendicular to the, for example, ground. So gravity force is clear, weight equals to mg. We can find it. Buoyancy force, I will talk about it. And I should talk about buoyancy and drag force. Okay, so let's go to talk first about drag force. Air resistance or the drag force, mathematically we can write the drag force like this is the equation of drag force. F equals to minus, because it is again motion, again the direction of motion, minus comes there, minus half rho a CD times V square. V is the velocity, and here when it reaches to the terminal velocity, we can say it is terminal velocity square. Rho is density of medium. What is our medium? Our medium is the surrounding atmosphere, air. Rho is the density of air, surrounding atmosphere of one droplet. A is cross-section. A is this area that is in contact with those air, surrounding air. And CD is the coefficient of drag, or drag coefficient. So drag coefficient is very important things to in creation of drag force, and generally we computationally find drag coefficient, because drag coefficient for different surfaces, if you move your hand in the atmosphere by the motion of one apple in the atmosphere, by the motion of this drop varies. Okay, it is not a constant. And from here we can this is when the surface are sleepy, drag coefficient comes down. For example, this is why the drag coefficient not only is a function of the material of the wall of the object. For example, a skin of a fish. When fish moves within the water, it likes when a drop moves in atmosphere. There is resistance between water and fish, and the coefficient of drag, this resistance is called drag force. And the amount of drag force increases if the skin of fish has lots of roughness. But when the skin is sleepy, it moves easily. This is why creature create very super slippery skin for a fish. The other factor that influence drag force or influence CD, in fact, is the shape of an object. If the shape is aerodynamic, like what we see in this fish, look, by aerodynamic, maybe you know this knowledge, or you have heard from other courses. When the water, this fish moves in this direction, okay, moves in this direction. Therefore, water should displace either in this direction and or in this direction. Based on several experiments that mechanical engineer works on, they found that this shape of this fish is the most aerodynamic shape that creates the minimum resistance, again the displacement of the, and what is already done millions years ago with our God. Or we can say, another in an evolutionary term, by the time fish community changed their shape in a way that they be more aerodynamic. Therefore, they decrease CD. Therefore they decrease drag force, and as a result, they can move faster. And this is why nowadays the shape of our cars goes to be in that or shape, to be more aerodynamic. Shape influences. And also, as I told, the material as skin is influences. Nowadays, you saw in, for example, in swimming matches, most of swimmers wear a kind of costume, very slippery, because it decreases drag coefficient, and consequently drag force. Therefore, they can move faster. Or even nowadays, very in modern cars, the paint on those cars is made from a kind of nanomaterials that allows air moves very very quickly than a regular paints that we have on our cars. So I talked about this issue, and also let's come back to the lecture. So we know we defined CD. I told rho is density of medium, density of air. And you see that when rho increases, drag force increases, yes, or decreases? Yes, increases, because if rho increases, this another example to understand the role of density of medium in calculation of drag force. Compare density of water with density of air. You know that density of water is 1000 kilogram per cubic meter, and it is 1000 times density of air. This is why you cannot ride your bicycle in water, or literally you 1000 times riding a bicycle in water is harder than riding a bicycle in air, through the air, because of density of medium changes. Higher density, higher drag force. So, and this is A, as I told, the surface that is in contact with the medium. For example, for this drop, what is the surface? This surface, yeah? This surface. Actually, this surface. The projection of a sphere, creates this surface. So already given here, drag force is upward, buoyancy is upward, buoyancy is displacement is upward, and gravity force is downward. Let's see these are true or not. Okay, for the first, gravity is what? WF or W equals mg. M equals rho v. This is v already written here. Rho v means m. We already know that. And g. That's okay. So this is okay. Buoyancy force equals to gamma v. gamma V or rho GV again. Here V is volume already given. For buoyancy force, I will talk in fluid mechanics more. This is therefore okay. And already I talked about this equation from here. This is drag force. And we know the CD now. We know the rho is atmosphere. Our medium is atmosphere. Density, the area given, and V square. Here V is velocity or terminal velocity. If I write the force balance at vertical or at y direction, I can write this equation: buoyancy plus drag minus weight equals to 0. Given those equations here, and if you simplify it, you will find such an equation which shows our terminal velocity. You see, I can get such conclusion. Terminal velocity is a function of drag force, function of diameter, and ratio of density of water to the density of air. And here you see the density values. And for drag CD, there are some experiments that give you some values to calculate CD. As I told, CD is a function of shape, function of material, or we can say is a function of a dimensionless number, which is called Reynolds number. It can be calculated for using this formula, where Reynolds number again is given with this formula, which you see is a function of viscosity also. Reynolds equals rho Vd over mu. This course is not about detail of these values, this formula. I just want to highlight that when a drop comes down, there is a drag force, resist motion downward. There is a gravity force, there is a buoyancy force, and when the droplet receives to its terminal velocity, we will have a balance between these three forces. Any question? And in previous feature formula, you saw that the terminal velocity is a function of diameter. Is a function of diameter, and in this figure, you see several diameters in x axis versus terminal velocity in y-axis. And if you see, when the diameter, we know that the diameter cannot be more than 6 millimeters, yeah, because flattened and divided. So the maximum velocity appears when the diameter is in the range of 5 millimeters. 5 millimeters. And you see maximum velocity varies maybe between 9 meters per second or 9.5, 8.5 millimeter per second. This is maximum velocity of raindrop. And this velocity is therefore velocity that one raindrop contacts with soil and splashes. Therefore, we can use this velocity to think about washing soil in our agricultural area or some other issues that called soil erosion. As a result of raindrops, we will have soil erosion, and this value is important in landscape design. So, in summary, terminal, we know that maximum diameter of a raindrop is about 5 to 6 millimeter, and based on drag forces, the maximum velocity of raindrop could be about 9 meters per second. Okay. Any question? No. So we get some knowledge about physics of precipitation. Now let's talk about application of precipitation in engineering, which starts with measurement, precipitation measurement. How we measure. You know what kind of precipitation we have, convective or orographic. These are some knowledge that mostly meteorologists deal with, not civil engineers. We measure the rainfall data, and based on those rainfall measured data, we are going to do our own works. Design of hydraulic structures, or design of control water distribution systems, design of flood control systems, and so far and so forth. So for precipitation measurement, when we are talking about measurement of precipitation, we should talk about 4 different kind of values that we can measure. First, amount of precipitation at one event, one rainfall, how much precipitation we have in an event. Second, intensity of precipitation. You remember definition of intensity? What was it? Amount per hour. Amount per hour is called precipitation intensity. Duration of precipitation, or duration, it is clear, the time, the period that a period that we have one rainfall event. It could be 1 hour, 2 hours, 1 day, 2 days, sometimes 4 days, 5 days continuously, sometimes only 10 minutes. Duration. Areal extent of precipitation. It means the area that we have precipitation on it. It could be a small catchment, it could be a large catchment, it could be a small village, it could be a big city, and other things. Precipitation events are recorded by gauges at specific locations. Okay, precipitation, first we are talking about point measurement, okay? Point measurement methods. Precipitation at one point. For example, at your city, at one airport, at one village. Okay, these are point precipitation. Point precipitation data are used collectively to estimate areal variability of rain and snow. Rainfall data are usually represented as millimeter per hour, millimeter per day, etc. You see, rainfall data are commonly presented in terms of their intensity. Millimeter per hour or millimeter per day, these are unit of intensity. But millimeter shows amount. And sometimes they shows in terms of mass. Especially in Turkey, I hear that usually reporters say that for example, yesterday we had 2 kilogram rainfall in terms of mass, 2 kilogram rainfall in that city. But we can transform those 2 kilogram rainfall to how many millimeters, because millimeters is more sensible to us. And we usually work with millimeters in hydrology. To measure at a point, we commonly use rain gauges. The precipitation height for a short period of time is measured by precipitation gauge or rain gauge. This is a classic rain gauge that you see in this figure. A cylindrical container that collects rainfall and measures its depths. It is non-recording gauge. The gauge is normally placed at the height of 1 meter above the ground surface. Simply, you see, we have a gauge. This is our gauge. It is graded. It is graded. There is a funnel within this cylinder, and you can measure the amount of rain that goes into this cylinder, and maybe this shows, for example, let's say 3 centimeters of rainfall. And you can say that at this point, rainfall amount is 3 centimeters or 30 millimeters. That it represents at some area around this point, not just that point, at area. One station, we say station, or one gauge, represent one area. This area could be small, big, and this is a classic rain gauge. And here I said this is non-recording. Non-recording means that this gauge gives you the total amount of precipitation at one event. It does not give you how much precipitation you had at every, for example, second, at every minute. For example, when precipitation event starts, its intensity increases, then decreases, then ends. But this gauge, or classic rain gauge, only gives you the total amount of rainfall after the end of the event. Therefore, we say it is non-recording gauge, non-recording gauge. We also have recording gauge that is commonly nowadays used in the modern cities, modern meteorology stations. Meteorology stations are places that we measure rainfall and some other meteorological variables. And it is called tipping bucket gauge. This is a tipping bucket gauge, that's a rain gauge that also measures timing and intensity. Therefore, we say it is recording gauge. It measures the rainfall with at least count of 1 millimeter and gives out 1 electrical pulse for every millimeter of rainfall. Let me explain you how it works. This is what we have in the station, what we have in meteorology station. The diameter is 20 centimeter, like standard classic rain gauge. And within this container here, we have such a system. And when water moves here, it moves downward, and from this hole goes here. And when it reaches here, oh, sorry, just a minute. When it reaches here, goes into this wing of this instrument, and when the amount of water seems to be 1 millimeter drop here, it moves downward, and a receiver receives one alarm. It moves downward, then this part comes up. For the second millimeter of rain, this wing goes down, another pulse goes to the receiver, again this moves up. It means by time it could be move up and down. If each down creates one signal to the receiver, it could, if their intensity is very fast, very high intensity, tipping bucket works like this, very quickly because intensity is high. But for low intensity, this tipping bucket works in that way. Look, maybe after 5-10 seconds, another 10 seconds, each signal shows 1 millimeter. After, for example, 2 hours, I have a rainfall, and after 2 hours, my receiver showed 20 signals. What does it mean? It means that each signal means 1 millimeter. 20 millimeter rainfall I had during 1 year. And the time between each signal can be measured. I receive one signal now, the other signal after 10 seconds, the other signal after 20 seconds. And it shows that how the intensity varies by time. Therefore, we say this is recording gauge. Again, these are instruments that we have in modern stations, meteorology stations, and nowadays commonly used at most of the countries. In some cases, when we have precipitation at far places, like at the top of mountains, at the middle of the forest, that we cannot every day go and see how much water we had it, and it is not possible to have such a wireless system, for example, to use signals transmission between the station and office. We install totalizers, and after or once a week or 2 times per month, or once per week or 2 times per month, we go and measure how much water we had in totalizer. But totalizers are designed in a way that what we earn, what it achieves from the atmosphere, does not evaporate. Using some oils within it, they avoid evaporation, and it is used when we would like to measure in a longer period. Okay, any question?
No, sir.
Okay, this figure shows location of some of the gauges, rain gauges that we have in Turkey. It is not entire. This shows the very famous rainfall stations, or we say meteorology stations, or it is called rain gauges. You see for example, in Antalya province, how many points we have, how many point measurement is done in this province. We have one in Gazi Pasha, one in Alanya, one in Manavgat, one in Antalya, Korkuteli, and so many. 1, 2, 3, 4, 5, 6, 7, 8, 9. At 9 stations, at 9 meteorology stations, we have tipping buckets in these stations, and in this province, we measure amount of rainfall continuously. Okay, so you see one is in Antalya, and this is the rainfall station or meteorology station of Antalya, which is called Murat Pasha station. You might see this station, and here you see different instruments are available at these stations, and these are tipping bucket. You see, these two are tipping buckets to calculate or to measure the point rainfall at Antalya. Also, they provide values of, for example, moisture, temperature of the sea, and temperature of the atmosphere. And these tipping buckets provide information for the rainfall, as I told. Okay, this is point all those either classic traditional rain gauges or modern tipping bucket rain gauges are used to point measurement. We have also remote measurement methods that we don't use rain gauge measurements. Can you guess what kind of methods we have as a remote measurement techniques? Any idea?
It might be some radar.
Radar, yeah, radar systems. Yeah, remotes, it could be using a radar or satellites. Radars or satellites are those techniques that we use to measure precipitation. Remote survey methods are indirect precipitation measurement methods involving radar and satellite precipitation measurements. You know, satellite technology is newer than radar technology. A radar or radio detecting and ranging device uses the fact that water droplets reflect radiation within a microwave range. A radar device serves as a radiation transmitter and receiver of the reflected energy. The intensity of the received signals enables determination of the amount of precipitation across the observed area, with a time lag corresponding to the location's distance from the radar. Yeah? For example, this radar transmits some signals to the cloud, and based on reflection of those signals from cloud, they can measure the amount of water that is possible to rain. Therefore, in the radar system, we measure from Earth again, but a big area in the atmosphere. But satellite, by contrast, the satellites uses another technology, as you see here. Satellite precipitation measurements are derived by geostationary satellites or satellite orbiting. Geostation, we have two kinds of satellites. One's constant, fixed at the moment, and just can, like this one you see here, assume it just monitor a given angle, yeah? That the other kind of satellites are orbiting around the Earth. They can monitor entire globe, entire Earth, orbiting over the poles along elliptical passes at a height of approximation of 900 kilometers. Unlike these satellites, geostationary satellites move at the Earth's orbited speed and therefore stay over the same Earth point. You know, geostationary, when I told this is geostationary, it is not fully stationary. There is not motion. This is, assume this is, let's show you an apple as a Earth. This is Earth, and this is, my finger is satellite. It moves when in a direction that Earth moves, okay? Therefore, it just monitors a given location, a given location. And if there is a cloud based on some signals that satellite receives or images receives, it analyzes and it gives us how much water it has based on other information. You know, satellites collect several information: temperature, wind, moisture, cloud thickness, blah, 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 blah. It can calculate amount of rainfall for 1 day, 2 days, 3 days later, or even, not just for now. And when we have even rainfall, they measure those records again. So this is not point measurement, it is called remote measurement. And in this table, you see some of the available satellites. Table belongs to 20 years ago, and nowadays we have several satellites, and most of the countries have their own satellites. meteorology satellites, but meteorological satellites of NOAA, Meteor, FY1, TRMM, DMSP, these are the satellites that provide rainfall. And sometimes I use those data. For example, TRMM data or NOAA data are available. And I can go to the website and see, for such a graph that shows, for example, at this time, how much rainfall I had at the globe, entire Earth, and how it varies. You see, these maps gives us some information about how precipitation varies across the world. And but satellite technology or radar technology does not mean that we don't need point measurement. We don't need stations, meteorology stations. Based on our knowledge, based on the gap that we have, still there are some errors in satellite measurements, even radar measurements. What they provide, what they give us, includes errors, mistakes, uncertainties, and with help of point measurement, we can correct those errors. For example, one of my master students works on this work. He selected 8 satellites that provides rainfall across Akdeniz Basin, and he also collected point measurements across this basin, and he compares how much differs these rainfall data. For example, satellite A or TRMM shows that in July 2020, in 1st July of 2020, there is no rainfall in Antalya. But point measurement shows there is 5 millimeter rainfall. It means that satellite is incorrect because the point measurements is the reality. We see it, okay? And he tries to find the differences and to say which satellite provides more accurate results and how we can correct the errors of satellites. Yeah, these are some topics relevant to this chapter of work that if you are interested also, you can work on such topic as a in a small scale, not working with 8 satellites, but working with 1 satellite, 1 station. You can do your senior project if you are interested in such topics. Okay, this is that's all for today's lecture, and next lecture we will talk more about how we apply this information in our engineering works. Any question?
No question, sir. Thank you.